Okay, so it's my pleasure today to introduce Vinayak Bhat. Vinayak received his Bachelor of Science and Master of Science degree from the Indian Institute of Science and Education Research, Thiruvananthapuram. I said the extra N. It's close. I've been practicing. Before coming to UK to join the Department of Chemistry in 2018. Since Vinayak has been here, he's been very prolific in the laboratory, as you'll see today. You can see this sort of enumerated a bit in that he has 6 published papers in the peer review literature already, with 2 more submitted. And there's going to be a lot more to follow, where there's already a few drafts that are coming. He's also given several presentations, including 3 contributed talks at American Chemical Society meetings. And for this work, he had just recently received was a 2023 Outstanding Researcher Award in the Department of Chemistry. Vinayak was also named in 2020 an Outstanding Teaching Assistant. So he received the Outstanding Teaching Assistant Award then. And that I want to just kind of highlight sort of in this last bit, in that Vinayak is an excellent teacher. He's an excellent mentor. One of the things that I don't think he'll talk about today that he does in all of his free time is that he's developed a series of workshops that he hosts online for a worldwide audience. So he really sat down and thought about these workshops. These workshops are geared towards teaching people how to do science, sort of at the convergence of chemistry, of theory and modeling, and of computer science. He's had these workshops live and then also recorded them. They're available on YouTube under the Chemistry with Code moniker. Vinayak has 1,200 followers. So go and sign up. So I don't know, how do you say it?
Subscribe.
Yeah, do the YouTube thing for Vinayak. He also took that and had a collaboration with the Center for Applied Energy Research and the Office of Undergraduate Research here at UK, and hosted a 2-Saturday workshop for undergraduates and graduates to learn Python programming. So in addition to being an excellent researcher in the lab, Vinayak has also honed his skills as a teacher and as an educator. So with that, it's my pleasure to introduce Vinayak. I'll remind everybody that this is the public portion of the defense. And so what we'll do is Vinayak will give his talk. And then afterwards, the people in the audience can ask questions. And then we will close the doors and hold the private defense. Okay? All right, this is the way. Ready?
Good. Thank you for the kind introduction. Further ado, let me jump right on to my dissertation. So my dissertation is titled Developing and Deploying Data-Driven Tools for Accelerated Design of Organic Semiconductors. To give a gist of what you're going to see in this talk is the tools that I have developed, which use computational methods, machine learning, AI stuff, and how those tools can be used by chemists, material scientists, to assist them in designing better organic semiconductors. The first 2 chapters of my dissertation give an overview of organic semiconductors and computational modeling methods. What I'm going to do over here in this chapter is to use this and lay the foundation of my research that you'll see in the upcoming chapters. Organic semiconductors have widespread application, and they are not something science fiction. Even my phone over here has organic light-emitting diode embedded in it, and there's a few solar cells out there, organic-based flexible devices, and they have wide applications. And the reason the research in this field is quite prolific is because you can change the molecular structure of these organic conjugated molecules. By changing that, you change the molecular properties and thereby tune the properties. And these could be done in the lab by simple alkyl substitutions or introducing a heteroatom like your sulfur in this carbon framework, or changing the framework itself by you can have a 5-membered wing or go to a 4-membered wing and make the changes in here. So all of those would give different properties as at the level of molecule. But the challenge in organic semiconductors is not just limited to the changes that you can make in these molecules, but also how they arrange themselves in solid state. And each over here, I've shown 5 representative examples of packing. There can be more. But each of these arrangements would give us a different property. Even though we have the same molecule in these different arrangements, they would give us different material properties. So the space to be explored is large. If we just think of combining these 16 molecules on top with the material arrangements at the bottom, we end up with 80. Not all of them would be possible, but it's a large space even with the small molecules. And if you want to understand how properties, the structure relates with properties, we need to explore a large material space. In the talk, I'll be referring to molecules. When I refer to molecules, I mean a single molecule that you see over here. And if I mean material, it's molecule plus one of these packing arrangements. Okay. So if we want to explore the space, we want to, let's look at a timeline for that exploration. This is a hypothetical one. You would start with molecular design in mind. You read articles and then come up with the changes that you can make at the molecular level. And in the lab, you might take a week to get the material, which is the solid state part of it with packing. And from there, again, a hypothetical timeline over here, let's say a week to get the material property out of it. And this is the experimental trial and error approach. And in a month, you would have maybe 2 materials over here and the property is estimated. But even for 80 of the combination that I showed before, it'll take a while to do it. So can we speed up this process? There has been computational modeling methods that can be applied to it. You can use Newtonian equations and model it. But if you look at the experimental accuracy and the accuracy from molecular dynamics, it's a large difference over there for electronic properties per se. And then let's say we introduce some quantum methods into it too. And we improve the accuracy, but also it takes more time now to get to the experimental accuracy. To get very close to experimental accuracy, we would need to use density functional theory, at least, which has some compromise on time scale over here, but we get somewhat close experimental accuracies. So if we use density functional based methods, which you might have seen if you read some chemistry or computational papers like PBE, B3lib, HSE, those are DFT-based methods that people use to evaluate properties. So if we now change from experimental trial and error approach to a computational approach, how would this timeline change? We could go from a material to its property in a day, because computers can do the job faster. And though DFT takes a while, it takes about hours to do it. And we can think of a day, less than a day, you get material property. The challenge from going from molecular design to material is a little bit hard. And even though we would use computational techniques, it's hard to find the exact packing that you saw over there. So it'll still take a week irrespective of whether you do synthesis in this hypothetical timeline or explore it with computations. With increasing demand, with cheap computing resources nowadays, and the emergence of AI and a lot of data and data management protocols like making the data findable, accessible, interoperable, and reusable. It's the FAIR principle that people have been using these days to manage the data, and that has evolved into the 4th paradigm of science, which uses all this data that is there and discover new materials using that data. So using something like machine learning models, artificial intelligence, and if you have a lot of data, what you could do is predict the properties directly from the data that you have. Example over here is, let's say we want to predict Y, which is the property, and X1 and X2 are the inputs that we have, or descriptors for the material. But we don't know what W1, W2, and B would be. But if you have large number of X1s and X2s and the corresponding Ys, we could train a machine learning model which tries to figure out what the W1s, W2s, and Bs would be. So given a new X1 and X2, it would predict a new Y, which would be the corresponding property. And this is very much abundant in our day-to-day use. We have Siri, we have Alexa. All of those are machine learning models that use some data, maybe from Wikipedia or Google web pages, and do a specific task. But if we could use our DFT-based data, that is for a material, and then train machine learning models, we could achieve an accuracy close to density functional theory, but at time scales which are close to molecular dynamics or semi-empirical methods. So this brings to the hypothesis of my research, which is if we have machine learning models which are trained on diverse data sets, the machine learning models could provide reliable predictions of properties. And if we look at this timeline of computational approach and try to replace it with machine learning approach, I hypothesize that from going from material to material property, we could do that in less than a minute. And going from molecular design to material, it may take an hour. I'll show why it is a little bit hard, but it's less than a week. So we had the initial timeline of 2 weeks from experimental trial and error approach, which we could essentially go down, which we could essentially bring down to an hour or so in finding new materials and its property. So this is what my hypothesis is, and I'll show you how I validate that. For first, we need a lot of data to train machine learning models, and this chapter, I'm going to show you how that data is generated. The challenge, as I mentioned before, is going from material to molecule to crystal, or material and then to property. The first part is the crystal structure prediction problem. Given a molecule, predict the structure. The second part is material prediction. And also there's another thing that is a molecule itself as a molecular property. So we need to also look at how good the molecule is. But we could save some compute time and only look at part of the molecule, which is responsible for most of the electronic properties. So from molecule, we can look at a chromophore, which is more relevant for electronic properties, and calculate the property. So to do this, we need information at the X1s and X2s. The input would be data for chromophore. For this prediction, if you want to go from crystal to material property, we need information from crystals and information from molecules to do the other prediction as well. So we need modularized data for crystal, molecule, and chromophore. And in order to get that, if I just have a crystal structure, what I could do is extract a molecule from here, and I have molecule and crystal relation over here. And from this, we can then identify the chromophore part, so we can get chromophore. And to predict the properties, I can use density functional theory to get the properties. And this is how I planned of creating the data set that is needed for the machine learning pipeline. To get the crystal structures, former graduate student Alex I had downloaded about 350,000 structures from Cambridge Structure Database, which has 1 million of experimental structures. I used that data and then scaled it down to around 56,000 crystal structures, which did not have any metal atoms and satisfied a bit more stringent criteria for organic semiconductors. From there, for those 56,000 crystal structures that I have, it ends up with 47,000 unique molecules and around 38,000 unique chromophores. And the smaller chromophores look like this, just two-membered rings in here. But the largest can go up to 24 benzene rings in a molecule. And benzene ring is just the 6-membered ring. So we can have 24 of those in there. Now that I have those molecules, crystals, and chromophores from here, I would need the data and the materials property and molecular property. To do that, I have designed this workflow where I can take the CIF file, which has the information for crystal structure, and clean it up a little, make sure that there's no disorder. When you determine crystal structure, you end up with some disorder, remove that disorder, make sure the structure is right, no missing hydrogens and all of those things. From there on, I divide it into crystals, molecules, and chromophores, and run high throughput calculations on each of those parts to get the data that I need. And all of this data is made accessible through a web interface, and the workflows do incorporate conversion checks, make sure it is running okay. If there are any errors, try to fix it. And this brings to the first tool that I would like to show, which is Ocelot. And Ocelot stands for Organic Crystals in Electronic and Light-Oriented Technologies. This is a database of all the high throughput calculations and those 56,000 crystal structures that you saw. It's accessible on this URL, and you can search for molecules in here. For example, it's searching for a molecule which is called pentacene. It'll show you a list of molecules, and then you can look at properties that you want for these crystal structures. And this is all in real time. It's fetching the data from the database and displaying it to you. And then you can even make plots or export the data as a Excel file. That has descriptors for HOMO energy, which is highest occupied molecular orbital, optical excited states, ionization energy, and about 2,000 descriptors in this database. It took a while to generate it, as I showed before. DFT takes a while to run calculations, and this was like millions of calculations, so about 1.5 human hours. So you can even search for crystals with same molecule or same chromophore, and it shows you like an e-commerce website where you'd have related products at the bottom. And that feature is also in this application that I have developed. It's a web interface. So we started with this timeline of 2 weeks, experimental trial and error approach. And if you use computational approach, we can make this 1 day for materials to material property. And for molecular design to material, even computational techniques take a week or so. So let me just keep this as the base timeline for the rest of the talk. So how does Ocelot over here change the timeline? In fact, it doesn't. It just helps you get more intuition about molecular design. If you look at articles that are published, they may be using different parameters for calculation, or experiments done with different solvents, for instance. But Ocelot provides all of the data which is consistent throughout. So that helps with molecular design and gaining some chemistry intuition or material intuition for design. So these computations that I showed you are complex and tedious. And if someone who made the material yesterday and asked me to run some calculations, I would be like, oh no, I have my defense schedule today. I can't do it. Even though it was 1 day for going from materials to property, there are some other practical things going on. So there's also some communication delays and other things. So how can we mitigate this? To do that, I have designed the second tool, which is Ocelot X, which does all of the high throughput calculations using just click of buttons. And as long as you have access to a high performance computer, you can just get this package from me, just put in the CIF file, and it'll run all the calculations for you. And if you want to make the data more public, what I've done is you can upload it back to the Ocelot for access again. We can update the website and show the molecule or the crystal that you have on the calculations. Going back to this timeline, the thing of going from material to material property would take a day, but you would need to find a different person to do it. But now the same person doing the experiments can go forward and do the calculations and get material properties with Ocelot X. There's the timeline shows material property, but we also need to look at molecular property, because if you don't have good molecules, we can't expect the materials to be great. So an experimental approach would take a week. And if we would replace it with computers again, computational approach, it would take a day. So can we now speed this up with machine learning? And that's what this chapter I'm going to show you about, is about wherein I do prediction of electronic, optical, and redox properties with machine learning. I have this huge data set with 25,000 chromophores that we looked at. So this data set contains properties including ionization energy, electron affinity, relaxation energy, and so on. There are 15 descriptors that you can think of, and these would be the Y for our machine learning models, and X would be these molecules. Because this is a diverse data set with up to 100 atoms, I hope that the machine learning model trained over here would be generalizable enough, and we could predict properties over large chemical space or material space in this case. So as I said earlier, we have a molecule, which is a 2D representation of it. And we want to predict the property, the Y, the 15 properties that I showed in the previous slide. So we have Y and we need those X1s and X2s. So how do we convert a molecule that looks like this to the X1s and X2s? So for this purpose, I use something called graph-based machine learning models, which convert this molecule into a graph where the atom is converted to a node, and the bonds between the atoms are the edges in this graph. And each of these edges, and the edges would have properties like whether it's a single bond, whether it's a double bond, and so on, while the atoms would have atomic properties, or what is the hybridization of the atom, what atom it is, and that information embedded into it. And that passes through this graph neural network blocks and leads to some transformed graph. And the way it does in this each block is you have those features, type of atoms and bonds. So it tries to pull in features from the neighboring atoms, like a social networking over here. So the atom is doing social networking and it gets influenced by the surrounding. So that's what is happening. And then that atom information is updated. And finally, you get a transformed graph from this input graph. And that is then going to give you the X1s and X2s for the prediction. And this thing is called message passing neural network of sending, interacting with the other atoms or the nodes in the molecule. And if that was too though it's sophisticated, this is what it does in simplified version. You have a molecule, you put it to the black box, the thing that I showed before, and it will give you a property. And we can use a different property, the 15 different properties, and train the machine learning model over here, so that the time we give it a new molecule, it will give us the property corresponding to it. So this is how it looks for the property prediction. R squares, some of them are good, some of them are bad. R squares in here, but does a pretty good job on some properties that are of interest over here, like ionization energy, electron affinity, the singlet energy gap, or the triplet energy gap. I would like to just focus on this too, a whole reorganization energy. Given a molecule, we can predict this whole reorganization energy, and I'll come back to this in the next chapter, why this is important. So this tool looks like the thing shown in this video over here, available online, open access. All you need to do is draw a structure in there just with clicks and select what property you want to want the model to predict, and it will predict it for you. And it's just like in a second or so, you get the property. This is available on this website over here. So with this, the timeline of going from molecular design to molecular property, which would take a day, now with the machine learning model that I just showed you, would take less than a minute to get to the property. And how does this affect the initial timeline of going from molecular design to material property? Ocelot over here provides data for molecules which are present in the Ocelot database. But what about molecules that are not present in the Ocelot database? We can use now the machine learning pipeline, which will give you molecular properties for molecules that are not in the Ocelot database and help you come up with new design principles. And also you can validate your intuition whether adding alkyl chain would be good or adding heteroatom would be good. Now that I've shown you how to go from molecular design to a molecular property in a day, can we do the same with material to material property? Sorry, in a second, in a minute or so, can we do that for material to material property as well? One of the critical property for organic semiconductors is charge carrier mobility. And what I'm going to show you over here is using machine learning model to make those predictions quickly. For charge transport, we can assume that there's a charge on this molecule and we want to push it throughout to the end, and there's transport of charge. And this can be modeled with different theories or different models that people have proposed. One is the hopping model. It hops from one molecule to the other molecule to the other molecule. This is more classical way of thinking. Or you can have the band transport, where you have quantum mechanical way of approaching this, that the electron would just like tunnel through it. Or there's an intermediate one, which is considering it hops and also it has this band-like transport, and that's called transient localization. Irrespective of what model we use to describe this charge transport, the electronic communication between two molecules is critical, and that's called electronic coupling. And if you do DFT-based estimates, it would take a day or so to get all electronic couplings in a crystal. And from there on, we could use the hopping rate. We can calculate hopping rate, which would eventually be used in calculating the mobility. For this, you would see that most of the parameters are constant except the lambda. And lambda is the reorganization energy, which is the energy that you would spend to move from this configuration where it's charge on this molecule to that molecule. And that's called reorganization energy. And over here, we neglect any effect of the surrounding onto it. So that's the lambda, and V is electronic coupling. So if you want to do these calculations with machine learning model, I already have a model as I shown in the previous chapter, where lambda was the reorganization energy. I did highlight that. So given a molecule, I can predict the reorganization energy. So what is now left is getting the electronic coupling. So to get the electronic coupling, it's a little bit more sensitive to positions in space. It's not just you have a 2D representation of a molecule, but you also have a 3D stuff to take into account. Where's the atom position in space? So this machine learning model does the similar thing as the 2D representation did, but now takes into consideration the positions and does the prediction. This model over here is trained on machine learning on a data set which is which has 438,000 DFT computed electronic couplings, and there is we do predict two properties, which one is homo-homo coupling, which is for hole transport, and LUMO-LUMO coupling for electron transport. It could be used in estimating electron transport. These models do have a pretty good R-square value when compared to DFT predictions, and mean absolute error of 3 milli-electron volts. And to validate how good they are in respect to DFT, what I've done is I've taken two molecules and moved them vertically and computed electronic couplings with DFT. The orange and blue is the machine learning. You can see the trend is pretty good beyond 3.5, and below 3.5 does not look so good. The reason being the data has only structures from experiments, and experimentally it's very hard to find structures where it goes beyond 3.5. That's because of the physics. It'll be not too close to get these parts. But if we move it laterally, you see that the trends are pretty much well reproduced with machine learning, and getting this whole plot with machine learning takes about a minute, while DFT would take about a day for me to do all these calculations. So now that I have electronic coupling and the reorganization energies from the molecular machine learning chapter, I could essentially use that and do the prediction. Over here shown is submitting of a zip file which contains the material. It's the material, and from there on, the code automatically extracts the dimers and calculates electronic coupling. So this is the structure, and over here are the dimers, and there's the electronic coupling you see. And using this electronic coupling and the reorganization energy, you can plot the charge carrier mobility in different directions. And this tool is also open access, and you can click on these view 3D buttons, and it will show you the two molecules that it has calculated coupling. Using this, I've screened over 60,000 crystal structures from the 350 things that we initially had that I initially got from a graduate student, Alexei. And from there on, this screening, as it takes less than a minute to do, I found out about 40 potential candidates for organic semiconductor application, which have charge carrier mobilities greater than that of amorphous silicon. So I've shown in this chapter how we could go from materials to material property, which took a day for traditional computational techniques. With machine learning, I can get the prediction within a minute. So the only part left in this timeline is going from molecular design to material. And that's chapter 6, where I'll show you something about interatomic potentials for crystalline organic semiconductors. So the challenge in going from molecule to crystal, generating structure in general, is the geometry relaxation part. And the relaxation is what needs a large number of forces. For example, if this is a molecule and we want to, let's wait for a while, it's a GIF, it'll load. Let's see. If we randomly place atoms in space and we ask it to relax, and we use density functional theory, what it's going to do is it's going to calculate forces on each of the atoms and try to move it in such a way that forces are minimized. And this takes a lot of time. This over here is a way of getting a relaxed molecule. But if we imagine replacing the atoms that you saw over here with molecules itself and placing them in all these positions and then relaxing them, it'll take a while to do all of this. And that's why DFT-based relaxations take like few hours to days and hinder the process of getting a crystal from molecule. It'll take a while, like a week or so to do it. So, oops. But if we have a machine learning model, that would give me the forces acting on each atom and not spend a lot of time on DFT-based forces acquisition, I could speed up this process. And that's what I'm going to show you over here is if you have a random molecule and place it in one of these positions, can we relax them faster and estimate which of the structure would be more stable and seen experimentally. For this, I use a machine learning model, which is again similar to the 3D message passing neural network that we saw for electronic coupling, but it also considers periodicity over here and gives me energy, forces on each atom, and also the stress on the entire cell. This model is trained on 2.5 million crystal configurations, and the results for these look pretty decent with energy predictions of 0.023 electron volt per atom. And this is less than the thermal energy, which is 0.025. So we are getting close to experimental errors in this part over here with thermal energies. And I will show you how this model can be applied for relaxing a crystal structure. If we start with a crystal structure of TIPS pentacene over here, these are the lattice parameters and the volume is 961. If I use density functional theory, it relaxes the structure. As I showed for a molecule, it does the same thing with crystals. And these are the parameters that I get. If I use machine learning, I get similar volume close by, so close by this alpha, beta, gamma. I think it's not showing well. Close by lattice parameters, and the relaxed structure, the one in yellow over here is the DFT based one, and the blue is the machine learning. You don't see a lot of difference in there, but if you look at the time it takes for machine learning, it took a minute or so to do this, but for DFT it takes like 4 hours for the same relaxation. And this tool for relaxation is available online. Over here, I show generating one random crystal structure, which is, the video is speed up 4 times. So you'll see it happening pretty quick. You have a crystal structure. I generate one random crystal structure, and we can relax the crystal structure. Though this is 4 times speed up, you'll see it is a little slow, but it takes less than a minute to relax the structure and give you a relaxed structure over here, and also the energy corresponding to it. So if you want to determine what would be the most stable crystal structure, it would involve relaxing maybe hundreds or thousands of these initial geometries and finding out which one is of the lowest energy, and that would be the stable structure. So, going from molecular design to materials with the machine learning model I just showed would reduce this time from 1 week and probably to an hour or so if we have to scan a large number of initial geometries. So this is how the timeline would be shortened. To conclude, I've shown you how we can use machine learning models to predict molecular properties, material properties, and also relax the structure. And this validates the initial hypothesis that I had, that if we have large enough and diverse data set, the machine learning models could actually do a pretty good job in speeding up the process. So I started with this initial timeline of 2 weeks to get to property, but with the tools that I've designed, we could accelerate the discovery and come up to an hour or so to reach to material property from molecular design. The Ocelot database and models have widespread users now. It's about 2,000 users who are using it from 48 different countries. So what's in the future for Ocelot? Right now, I would be interested in generating equilibrium crystal structures. I just showed you one structure and how we could relax it, but we could do that for thousands of initial structures and find the most stable one, and try to include dopants or interaction with device substrates. Right now, everything is in pristine form, and there are no dopants. And it would be good to add this validation step in between. Right, all I've shown is data, model, and predict, but use experimental data to validate it, and then close this loop would be the thing to go about for Ocelot in future. All these are the publications that have resulted from this works and these are at various stages of publication. Some of them are published, some of them are under revision, and some of them submitted. In addition to what I've shown over here, there's a lot of fantastic collaboration that I've been involved with and other projects. And even those publications are at various stages of publication. All this work would not have been possible without funding from a National Science Foundation. And the compute resources were from XSEED and Center for Computational Sciences. And I would like to thank Dr. Chad Wisco for his advice and guidance throughout my PhD, and both in science as well as life in general. And thank you, Dr. Wisco. I would also like to thank my committee members, Dr. Anthony, Dr. Beck, Dr. Graham, for the advice and making sure that I'm on track for my PhD, and Dr. Johnson for agreeing to be an outside examiner for this defense. There are a lot of collaborators whom I worked with from NYU, Stanford, Princeton. I would like to thank Dr. Bhaskar Ganpati Subramaniam from Iowa State University, who has been of tremendous support for the machine learning projects that I've started working on, and most of the things that you have seen now. A big thank you to computational staff, Vikram and Bhushan, without whose help all these calculations or setting up of the website would not have been possible. And former members and present members at Wisco Lab, whom I have collaborated with, worked with on various projects, and thank you for making the lab so fun and to work with, and all those fruitful discussions. With that, I would like to thank you for your kind attention, people here in person and also on Zoom. I would be happy to take up any questions. Thank you.